My name's Aram Harrow, and I'm a physics professor at MIT, where we are right now.
And which department?
In physics.
Nice, cool. Well, I would start with a very general question. So what is your opinion about the possibility of quantum computing or quantum physics breaking the cryptography as we know today, and especially the factoring problem?
Right. When I started this field, it seemed unclear if these things would ever get built, but now it really looks like quantum computers are on their way, and it does seem likely that people will be able to scale them up, and companies are working very hard on doing that. And so I think we should expect factoring to be solvable by quantum computers before too long, and that will mean we'll have to think about changing the codes that we use.
How long it's gonna take?
Yeah, everyone always wants to know how soon will we have quantum computers.
I mean, it's a bet.
Yeah.
I hear many different expectations, but I wonder your expectation.
Yeah, and it depends if we keep on pushing as hard as we do for them. But I think at the rate we're going, I wouldn't be surprised in 10 years. Maybe earlier if we're very lucky. It could be longer if companies decide not to invest so much. It can take longer.
We never know when a breakthrough might happen.
Right. Well, and to get there, we still need many, many little breakthroughs. So we've always had them before. The qubits keep on getting better because people keep on solving new problems, but people might not solve them. There's no guarantee that we have to keep on improving them.
Yeah. Did you read the new paper that says that 1 qubit might be enough, but it takes a lot of energy? That's kind of like a new update on that.
Yeah, I think that doesn't change things too much. I don't think it's really a practical approach. I think we still need a lot of qubits if we want to do it in a practical way. But that number is starting to get within reach.
And do you think that all this research on quantum, so not just the computing and not just the number of qubits we might reach, could also reveal something else in mathematics and maybe something that solved that factoring problem?
It's possible. I think that in general, thinking about quantum information has been a really productive way of thinking about a lot of different things. For example, many-body physics. We know that entanglement plays some kind of role in materials, and quantum information has helped give us a language for that. And other problems in math and computer science has been helpful for factoring. People have thought really hard about factoring in particular. For thousands of years, people have thought about it, and recently, there's been a lot of attention to it. So I'd be surprised if there was some kind of, major thing that we've overlooked. So it's possible. Quantum computing has given us new perspectives on a lot of things. Factoring is one of these problems that's been thought about so much. I think there's less avenue for new surprises, but you never know.
It's still an assumption.
Yeah, right. That's the thing about all these problems. So why do we think our codes are secure? Well, we think that the computers we have now can't factor quickly. Why do we think that? Well, people have tried hard to find factoring algorithms, and so far, they've only made so much progress.
I was reading this book, The Structure of Scientific Revolutions. And of course you know it.
Yeah.
And it's very interesting to see that every 100 years or something, there is this scientific breakthrough.
Yeah.
And everything that was thought obvious is not anymore. Right. And there were all these assumptions that all of a sudden fall.
That's
completely. And so that's why when I hear that, the factoring problem is unsolvable, it's secure, but then I think about that book and say, wow, things can change overnight completely.
That's right. Every limitation that we believe there is to computing is one that we generally cannot prove, but really it just reflects the limitation of our knowledge. So we know with a computer you can do some things quickly, like find the determinant of a matrix, solve certain problems. And then other things like translate from one language to another one or generate images. We're just now finding out how much computers can do. And you never know what people will invent next. Maybe nothing. Maybe we're all done with new ideas, or maybe this is just the beginning.
Right. So what are your hopes for the post-quantum cryptography and also the quantum cryptography?
Well, I guess I have a few hopes. I hope that the world can transition in time to some secure post-quantum crypto system. And part of that means quantum algorithms researchers like me need to think hard about breaking them. With these post-quantum systems, again, it's an assumption that they can't be broken. That we assume they can't be broken by a classical computer, and we assume they can't be broken by a quantum computer. So I hope we'll start to learn more about that. And quantum cryptography seems less likely to be practical, but it would be interesting if something could be made use of there. And I'd also love to see if there are more applications of quantum communication, not only for cryptography.
Yeah. Also, because in the case of breaking the public key encryption with the factoring, solving the factoring problem is kind of like an apocalypse,
right? Pretty
much in these days.
If it were sudden, right? And if you think about computer security, we're always finding there's a bug in Windows, there's a security hole in this or that. Usually they're 0 day. We find out and they're already being exploited. Here we have so much warning, so I really hope that we'll be able to change our systems in time for it.
In your work, are you interested in solving these kind of problems, or?
I am. I haven't had a lot of ideas for breaking a post-quantum crypto system like lattices. If I had an idea, I would pursue it. I've done things that are more adjacent to it, like developing error-correcting codes might help build a quantum computer that would break these things, for example. I haven't thought about lattice crypto systems directly, but if I had an idea, I would definitely pursue it.
So you are more interested in breaking than making new algorithms?
Oh, sorry. I'm interested in making new algorithms for a lot of things. I'm interested in quantum algorithms to simulate quantum systems like molecules or a material. I'm interested in quantum algorithms for optimization problems that you might use in machine learning, for example. And those I've actually worked on. I would also be interested in quantum algorithms for breaking codes. I just haven't had a promising enough idea there to pursue, which I think probably many people in the field would say that. Many of us quantum algorithms researchers, if we had an idea for breaking a lattice crypto system, we would like to explore it. But there just have been very few ideas for breaking it.
Yeah, I mean, a few rooms down this building, there is Peter Shor.
Yeah.
But his algorithm was made so long time ago.
Yes.
It's kind of surprising that nothing else came up until all this time. Or do you know any other algorithm that perfected the Shor algorithm?
There are many other algorithms that have been invented since Shor's factoring algorithm. I think the factoring algorithm made the biggest splash because it was such a surprise. You'd think, okay, a quantum computer, sure, that can help simulate a quantum mechanical system. Maybe that's a big speed up, but it's conceptually not a big surprise. But I think it was a really big surprise on two levels. The first was, what is Schrodinger's equation for quantum mechanics? This seems to govern atoms and light and chemical reactions, and this seems to be something about physics. What did it have to do with factoring numbers, number theory, and codes? It just seemed like such a jump out of the blue. And then the other surprise, of course, is that these cryptographic implications are of course a big deal. They were a big deal 30 years ago when the algorithm's invented, and they're getting closer to relevant now. There have been other algorithms which I think have been less of a surprise, because once you've seen Shor's algorithm, you're maybe less surprised by other things that come along.
Yeah, so there have been new algorithms, but Peter Shor is the big one, is the most important one because it was the first.
Right.
But even this new one that is using 1 qubit is a kind of a breakthrough in a way. I mean, it's still theoretical as much as Shor algorithm, but it's still something that can also be that other new algorithms might be invented sooner than we expected.
It's always possible, The thing about algorithms is they only get better, right? So it could be that our level of algorithms will stay the same, or it could be that there'll be someone will come up with something new tomorrow. So, Yeah, you can't. It's hard to say.
And thinking about the development of other computing in history, and especially from analog to digital,
Yeah.
and that kind of breakthrough that also made possible all the development of digital technologies.
Right.
It's actually there was quite a long time researching on the creation of the transistors.
Right.
But then from the transistors to the microchip was such short amount of time.
Yes.
Do you think that can happen again in quantum computing or quantum logics or something like that?
It could. Yes, arguably. So there's something called Shulkoff's law, named after Rob Shulkoff, a superconducting qubit experimentalist from Yale, where he plots the improvement of qubit lifetimes. And the reliability of qubits has been improving much the same way, at sort of a similar speed to Moore's law. Moore's law says that we get more and more transistors per chip, and Shulkoff's law says just for one qubit, its lifetime has been exponentially increasing. And so I think there has been a steady progress, just as there's been in classical computing. It's just taken a long time because there's such a long way to go. The first qubits were just so low quality, and the quality we need for a scalable quantum computer is really quite high. And we're sort of at the threshold of that, but it's taken a long time.
At the same time, the breakthrough might be not in computing, but it might be in the logics of quantum. So once we know how the quantum logic, the quantum math works, then we don't even need the quantum computers. We might just need the regular computers, but to use a different kind of logic. Is that something?
We could come up with a new algorithm for our existing classical computers. That's absolutely possible. It seems I wouldn't put my bet there because people have been thinking about that for a long time. Many thousands, tens of thousands of smart people have been thinking hard about how to better use classical computers. So again, it's always possible that there'll be some new area of math, some paradigm shift, something that everybody's overlooked, or something that the entire field needs. I can't say it's impossible, but I think it's not something that I would bet on.
And going back to the science, so we also explored the ethics of quantum supremacy, if we want to call it in that way. And you are a scientist and connected to the scientific community. What do you think is important to consider in the ethics of quantum supremacy?
Yes, so I guess by quantum supremacy you mean building a quantum computer that can do something beyond the reach of classical computing.
Yeah, and be the first creating that. So reaching that supremacy and be the one owning that power, right?
Right. So I think it's a good question. I think it's a little bit like any technological development. It could potentially shift the balance of power. It could be destabilizing. It could be something that countries might come to some agreement about, and it could, and when there's new technologies, it can potentially shift the balance of power. I think that for quantum computing, I think it's likely that new codes will be widely adopted before large-scale quantum computers are built, and so I think that impact will not be so enormous. I think there probably will be some effect there. Then it's of course there'll be some impact on industry. The country that builds quantum computers first might set the agenda for the field. They might have an advantage in new kinds of material science, in biotechnology, in chemistry. But I think you have to look at it within the context of industry overall. Right? There are many ways in which industries advance, and I think quantum computers will be part of it.
Yeah, but whoever have that first breakthrough in this technology should be open to share and to make it available to everyone, right?
I hope so. Yeah. I mean, we see, international trade and cooperation is something that comes and goes, and I hope that Right.
Do you think in science there is, there are some ethics in science, but there are also some committees or organization that would make sure something like this needs to be, they cannot enforce or force anyone to open their secrets.
Right.
But is anything specific in these questions?
Well, the quantum computers that we're on track to get are very expensive, and the academia is no longer leading the development of large-scale quantum computers. What's being developed in universities are a few qubits and some techniques for them. The large-scale quantum computers are now being built by industry, and so they, of course, will want to sell their machines or sell access to their machines, and I imagine that they will push to avoid things like export controls. It would be in their interests for it to be widely sold and widely used. I think it would be, scientists like me, I think we love to collaborate internationally, right? We want to share our ideas. We want to learn from the best people in the world and work with everybody. We don't want there to be walls between countries, and we don't want to be sort of locked down by proprietary technology and things like that. And companies that are developing the quantum computer, they partially align with this, and they have their own goals. In this case, they've put a lot of money into it, and they hope to make money back. And so I think this means that they will want everyone to have access to it, but they probably would like to be paid for that access. So I think that's probably what the future will look like.
And there is nothing that can avoid this privatization of this scientific research or something.
Well, I think certainly governments could develop a public sector alternative, which is is a bit true for anything, right? So for pharmaceuticals, the government, we could leave it to the private sector to develop new medicine. We could have the government develop its own, or do something in the middle where maybe the government decides to pay private companies for some things to be made public and leaves other things to the private sector. So I imagine we'll see something a little bit like that. For example, large-scale computing is often done by the Department of Energy. They have these supercomputers that are used to simulate quantum systems, just the classical supercomputers. And so they are likely to invest in quantum computers to simulate quantum systems. And then these quantum computers would be available to any researcher. You would just make a proposal, make the scientific case for why is this interesting, and bid for access on it, just like you do for a telescope. You make your best case for why you think your use of the time would be useful. So I imagine something like that will happen, and at the same time, there'll also be investment from companies. And it's not the sort of thing that can really be monopolized, right? Once we learn how to build them, eventually, I hope the cost will go down. The first one will cost quite a lot, and eventually it'll be like the computers we have on our desktop. They'll get much more available eventually.
Yeah, but there might be 10, 20 years in which private companies own quantum secure networks, quantum computing capabilities. Right. That might be actually a scenario, probably is going to be really like that, and maybe pretty soon too.
Yeah, it'll be...
Maybe.
Yeah. Quantum networks is a good question. It depends if the way we're achieving security is with quantum communication, which will cost a lot more, or if we'll have some post-quantum cryptography, which you can just use our existing networks for. I think that one's maybe more likely. Yeah. And then will quantum computers, probably those will be dominated by, certainly they will come from industry, and so then industry will hold a lot of the cards. And how we navigate that will be a collective decision, I think.
There might be some post-quantum cryptography already implemented in some browsers and some chat apps.
Exactly.
But at the same time, to upgrade to post-quantum cryptography and even worse in quantum cryptography is going to take much longer because we need to upgrade all the applications. What do you think about that?
So this is a little further from my field. I'm more of a...
Sorry.
No, I'm happy to speculate. I think it's... So, you know, since my specialty is to develop the quantum algorithms, and I think you're absolutely right. The upgrading will take some time. And my understanding of it is that software is upgraded easily. Every time you quit Chrome and reopen it, they've updated to the latest version. That happens very quickly. But hardware takes longer. You know, your doorbell camera, you know, these embedded chips and routers and so on, those probably sit there for a very long time. And so things like that will take longer to upgrade. And so that's a question which is a little beyond my expertise, but I do agree. It does seem like it'll take a long time to make this upgrade.
So are we running late? Maybe.
That I don't know. I don't know actually how far along things are going. It's a good question. It's good to have a lot of warning, right? And so part of that is it's really good that we know about Shor's algorithm, right? And so we know that we need to move to codes that are resistant to it. And I think that's also why it's important to do things like researching quantum attacks on other cryptosystems. For example, we want to move to a lattice cryptosystem because we think that's going to be quantum resistant. But is it quantum resistant? Who knows? The only reason we believe it is that people have tried and failed to break it with quantum computers. But not that many people have tried, and we haven't tried that hard. There haven't been that many ideas. So it would be, that's something where if I had a worry here, it would be that we haven't tested these new post-quantum cryptosystems enough. That's, I think, where that will deserve some attention to make sure that we can be confident in their security.
I am so glad you're saying that because in many interviews, some people are very confident that everything is already solved because post-quantum cryptography is already there, NIST already did the job, everything is fine, but actually we don't know the timing, we don't know if these things work, so we don't know how big the problem is going to be. I mean, the problem is huge, but we don't know how long it's going to take to solve the problem at all because of all the upgrading and migration. So I am so glad that you're concerned. Of course, warning is the first thing we have to do, also because these things might accelerate anytime soon. And by the way, were you involved in the error correction development?
I wasn't not one of the early developers. I've worked on quantum error correcting codes, but I wasn't one of the inventors of it.
And so do you think, because this is very recent, right? The achievement that they were made in the last year, actually.
Well, the demonstration of it was recent. The codes were invented in the mid-90s. No, so that's 30 years ago.
So now in practice they are implemented.
Now they're being, So from the beginning, we knew the theory of it. But the hardware was not yet at the point, actually, and the hardware was at a point where you could implement a quantum error correcting code, but it would make things worse if you did. So the problem is, let's say that each gate is pretty unreliable. And to implement the error correcting code, you have to do, 30 gates. And so then that only improves things if those gates are reliable enough in the first place. This fault-tolerant threshold that people talk about, and so it's only recently that we've crossed that.
But now it's done, so it's already a big development, right?
Absolutely, yes. And it's done, but the trick is now to chew gum and bicycle at the same time, right? To keep these high-quality qubits while continuing to scale up the devices. And that's kind of the challenge that people are grappling with.
And do you like more the quantum computing with the optics laser or the what else the atoms or which is the one you prefer?
Well, I think the neutral atoms are very exciting for the fast progress they've made. I think the leader is still superconducting qubits. But it's a very close call, and
The optics, you don't like optics, lasers?
I like them. I think they have a long way to go.
Oh, really? Oh,
Yeah.
they seems like the easiest way, also easy to control because they don't need to be cooled down, right?
Right. The room temperature is really great. The some things about them are really great. The problem is that photons don't like to interact with each other. You shine two beams of light, they pass right through each other. And so the interaction part is a little bit challenging. And there's some other challenges as well.
They use the diamonds to have less
Right.
noise, and they say
Right.
it's the best thing to use. But I think everyone has different opinions.
Yeah, I'm not an expert on that hardware. I do know that they can get the noise very low. And they've made a lot of progress there. So there's definitely potential, but yeah. So the other thing that's good about the photonics is it could scale very well. So if they can solve some of their problems, they could, even though they haven't shown many qubits so far, they could rapidly get a very, very large number.
Right.
So I think it's something to watch out for.
Yeah. And at the same time, this quantum law, quantum physics is everywhere. So once we figure how it works, then we can use not any material, but any particles or other ways to do computing. Do you think that could be a thing?
I think that, well, right now we're pursuing several approaches. I think one of them will win and will leave the others behind at some point. Even though quantum mechanics does describe everything, it's pretty hard to make a quantum computer because you need many things at the same time. The main challenge is you need to be able to control something and have it isolated from the environment. And having one or the other we can usually do, but having both together, that's kind of the difficulty.
At the same time, they say that quantum mechanics is in nature, is everywhere. So,
of course, yes.
Like plants have quantum mechanics.
Right, yeah, this table is quantum mechanical.
And these things, they don't need to be in a controlled environment. They just do that by themselves.
Of course, yeah. No, quantum mechanics describes everything in the universe.
So if we figure how these things work, then we can have repeating that computing without controlling the environment because we just know how it happens.
Maybe. Let me give you an example. So we know that if you just take normal computers, in theory, you can build a normal computer out of billiard balls. You have billiard balls arranged just the right way. You shoot a few of them in, and if they collide, they bounce off each other in certain ways. And the cascade, like a Rube Goldberg machine, will perform the calculation, the same calculation that's running your Zoom meeting or processing an image. You could do that with billiard balls, right? And in principle, also, you could do it with streams of water. People have actually implemented very small computations. And the way it works is if you have one stream of water, it goes this way. If you have one stream, it goes that way. But if you have two, they meet in the middle, and then it goes straight down. So something different happens if you have two than one. And you can build up gates out of this. You can build up a little addition circuit, multiplication. Any computation can be done this way. And then you could say, well, what about a glass of water on my table, and I stir it with a spoon, and there's turbulence in there. And the turbulence is so complicated that it's hard to simulate on a computer. It's doing something that's hard for even a supercomputer to model. So there's something computationally very powerful happening in that cup of water. So could that be my new computer? Maybe that could be my supercomputer. And the problem is, we don't have good control over it. You can get turbulence a lot of different ways, right? You drive your car, you get turbulence. You move a spoon through water, you can get turbulence. And to simulate it, maybe there's billions of different variables that the computer would have to keep track of. But that doesn't mean that by turning your spoon in water, you can control billions of variables. And if you could, you probably couldn't keep control over those. Those billions of degrees of freedom would get lost into even more degrees of freedom in the water. So what our digital computers do is you have billions of degrees of freedom that you don't lose track of, right? Each one of them is protected. That's the beauty of digital logic, is that every one of these degrees of freedom in the computer is actually pretty safe. It's unlikely to have an error. And so when you have some quantum information in nature, something very complicated is happening, but it's hard for us to control it with as much precision as we can a computer. The time when when natural systems can help us a little bit more, which I think has been a dream of quantum computing for a long time, is a topological material. And so there are some examples of this. If I have a sheet, let's say this table were metal, and I apply a magnetic field pointing up, then and I put a voltage on each side, then there'll be a current that runs along the edge of the table. And the resistivity turns out that will be quantized. It can only be certain integer multiples of a certain number. And this is something which, even in a large, dirty material full of imperfections, not at absolute zero, but at some reasonable temperature, can be demonstrated to very, very high precision. And people have used it to measure physical constants, like the fine structure constant, to very, very high precision. And the reason for this is people call it a topological effect, because the current is not running through the body where there's a million paths it could go into. It could scatter off of many impurities and so on, but it's forced to run along the edge. And if there's a bump in the table, it will follow the bump around. And if the table changes shape a little bit, wherever it goes, it will still follow the edge. And so there are other examples of these topological effects in quantum materials. And the topology gives it a certain robustness, because if the table changes shape or there's some more impurities, it doesn't matter. It still has an edge. It has one edge for the current to follow. And so people have hopes of building qubits out of this and having topologically protected quantum computation.
Yeah, and that topology is also in any magnetic field or growing material in many other parts, because it's part of quantum mechanics, of course. Just one question two questions, and then we're done because it's getting longer. The first question is around going back to the factoring problem.
Yes.
Do you think that the number theory might be revolutionized through this quantum math and quantization? So quantizing information might provide a new number theory?
I think there actually are important connections between quantum physics and number theory. Actually, it hasn't so much happened via Shor's algorithm, but by looking at this basic equation in math called the Riemann zeta function, and the zeros of that connect to some things that happen in quantum chaos. So we talked about turbulent systems. If you have a quantum chaotic system, then there's some mathematical properties of that relate to the Riemann zeta function, which has some connections to number theory. And so there have been very beautiful and deep connections like that.
And that theory is connected to prime numbers.
Yes,
right?
Exactly. Yeah. Yeah, there are many beautiful connections. In my own work, I've studied what seemed like a basic quantum information question, which is, if you have a state, can you check whether it's entangled or not? And this turns out to have connections to many classical computer science questions of optimization, and something called the unique games problem. And there are many surprising connections that you can find. And I think it's a little bit like you were saying about new paradigms, that quantum mechanics and quantum information provide some new paradigms that can make unexpected connections.
So if the prime numbers are entangled, we're fucked.
Could be. Yeah.
No.
Yeah. Who knows? Who knows? Yeah.
Yeah. Cool. And the other question is really the final question, but it's actually whatever you want to say. Maybe you had something in mind you want to say during this interview, or...
Well, it's
about the ethics, about the physics or the computing, anything. If you didn't have anything, it's fine. I don't think I have many other questions actually. We're pretty much down.
Well, I have maybe a few disconnected things to say. One, in terms of, how do we prepare for a post-quantum future, I think we should not think of quantum computers as the only surprise that will come up. So I think when people think about how to change systems, probably we should figure out a way to change them that you could keep on upgrading them in the future, because I think we should expect a steady stream of surprises. And the other thing I'll say is that, as you've alluded to, quantum information is giving us a lot of new ways of thinking about things. And one of them is quantum mechanics itself. Quantum mechanics just reached 100 years old. And the way people have thought about it for so long has been shaped by the pre-quantum computing technologies. It assumed that the way you could probe quantum mechanics experimentally was by maybe smashing particles together in a collider, maybe shining light on an object. It didn't assume that we'd have the kind of precision control that we will expect in quantum computers. And in that way, even before we build a quantum computer, just thinking about it has really changed the way we think about quantum mechanics. And so I think it will keep on giving us conceptually new things, which I hope will be as unpredictable today as the implications of quantum mechanics have been 100 years ago.